definition of isomorphism. So, I won't be making distinction between can you close the door? I won't be making the distinction between geometric and abstract. Okay. So, I want to be vague when it comes to that. So, what the main idea is, if you have a simplicial complex K and a complex K prime, let us say this is on the vertex set V, this is on the vertex set V prime. Okay. We say that K and K prime are isomorphic if there exists a map phi from V to V prime, okay, such that so let me write like this. V 1 V t is belongs to K if and only if phi of V 1 phi of V t belongs to K prime. Okay. So, basically, I mean, this means if the complex is isomorphic, basically it means they are the same thing, just the vertices have been labeled in a different way. That is it. A different labeling of the vertices you have. That is it. Okay. So, like if I say this complex, let us say 1, 2, 3, or other than that I write 3, 2, 1. Are they different? Not right, and there is I can relabel the vertices on the left to get this, right. And ideally you do not want to make distinction between isomorphic simplicial complexes. Good. Okay. So, I want to define an object which is called nerve. Okay. It has a very natural connection to. So, like nerve is Delaunay complex is a nerve of the Voronoi diagram. Okay. So, what do I mean by that? Let us say you have a collection of, so let us say S be a collection of subsets. Now, let us say subsets of first 1 to n numbers. Okay. These are subsets. Okay. So, Si subset of. Yeah. So, I mean it does not have to be first 1 to n. So, let us say make it, because we will be working with geometric things. So, let us say some omega set. Okay. Think of it whatever you like, think of it first 1 to n numbers, some region in R2, whatever. Okay. So, for each Si, so now what I want to do is, I want to build a nerve complex of S, this collection, it is called nerve S. So, first let me define what will be, see this will be a simplicial complex, okay. Nerve of S will be a simplicial complex, it will be an abstract simplicial complex also. From the first we will define the abstract simplicial complex, that is the easiest to define. Okay. So, this abstract simplicial complex, we have to define what will be the vertices of this simplicial complex. I say the vertices of the simplicial complex are S1 to SL itself. Sounds a bit odd, no? So, let us say, okay, let us not define in that way. So, let us say I have separate points V 1 to V, not points, but okay, some symbols V 1 to V L, okay, and V 1 V I basically represents S I. S I is like a, okay, V I and S I there is like 1 to 1 correspondence. Say S I and V I are same thing for me. Vertices are sets. So, I will come to it how this plays. So, just so forget about vertices are set, that is why I have defined these points V 1 to V L. Okay. So, what are the simplices that will be in the nerve of S? This definition. What are the simplices that will be in the nerve of S? So, I will say sigma subset of belongs to nerve of S if and only if intersection I for intersection all V I belonging to sigma S I is not equal to empty. Also, before I give this definition, just one small comment. Okay. So, the theorem, what did we prove at the end of last class? We proved that any t dimensional abstract simplicial complex can be has a geometric realization in R 2t plus 1. Okay. So, what can you see? So, I can think of a graph as an abstract simplicial complex. How? I will include the vertex set, vertices in the set like singleton vertex, I will add those elements, then I will have the edges which are anyway 2 sets, and I will add the empty set also, the way we are doing it. This will define a graph completely. It is a simplicial complex. So, previous result implies what? Any graph has a straight line drawing in R 3, right. Does not matter how many edges you have, does not matter how many vertices you have, okay. Any graph, okay, finite graph, I mean the vertex set I am assuming is to be finite, has an geometric representation, straight line drawing in R 3, right. That is basically the consequence of the previous thing, okay. That is a smaller consequence. Okay. Good. Pardon? No, yeah. So, what is the maximum dimension of a simplex in a graph? 1, right. Edge has 2 vertices, right. Remove 1, the dimension is 1, right. Okay, good. Yeah. So, now let us go back to the nerve here again. So, let us take one very nice example that comes up all the time in topological data analysis. So, normally I like to call it computational topology, but to make it sellable to people who fund projects, we call it topological data analysis. So, let us say you have points in P1 to Pn, points in Rd. Okay. So, this is used all the time for analysis. Okay. So, and you assume it is on these points are like dense sample of some nice objects that is embedded in Rd. Okay. Maybe a curve, think of like a curve embedded in some R100. Okay. Obviously, this curve may be complicated, it is hard for me to store, right, but I want to like understand the properties of this curve. One of the ways you do it, you sample lot of points from this curve, and using the samples you try to learn the properties of the curve. Okay. It can be surfaces, it can be manifolds, many other things, okay, other geometric objects. Okay. So, you want to, this is mostly used to understand topological features of objects, okay, whatever that means. Okay. I do not want to get into that. But normally, one of the simple examples, like simple way to do it is, you have these endpoints. What you do is, around each point, you build a ball of radius alpha. Okay. So, you have these points, and you want the alpha to be small compared to the complexity of the curve or this geometric object. Okay. See, intuitively, if the point set are densely sampled and if I keep varying alpha, I hope to get some alphas for which the union of the balls if I take, Okay. That will kind of be a good approximation to the curve union of these balls. Right, makes sense. But keeping union of balls are super expensive. If you like, you have done the R2 case, that itself is something. So, where there was one tutorial exercise you wanted to find, like you are not even asked to keep like a structure of union of balls. What we are asked to keep? Even like the union of the volume, that required you to compute what? A Voronoi. Voronoi in high dimension is like prohibitively expensive. No one is using it. The complexity of the algorithm will be like n to the power 50. Okay? I mean, most of the time you want something to be like not even n square. So, what should you do? There is a complex that is defined, what is called check complex. The accents I do not know, but check complex. So, you call check complex this for this family of balls. So, let me write F as the family of balls. So, like this. Okay. So, how do you define it? You say, so this check complex will basically, it is an abstract complex first. This has a geometry representation, but forget about that for the timing. It is an abstract complex. What you do is, you keep subsets of P1 to like the subset of some subsets of P1 to Pn. It is a simplicial complex also. Okay. So, you will keep a simplex sigma will be in check complex if the balls centered at the vertices of sigma have a non-empty intersection. What do I mean by that? So, this belongs to this if and only if intersection Pi belonging to sigma B of Pi alpha, okay, is not equal to empty. Okay. So, now the natural question to say is, okay, I mean, if you can assume some general position assumption on this point set, you can have a geometry representation of it also in some RD. Hope to, okay. Sometimes not, but it won't matter actually. Okay. But yeah, not function, check comp. So, F is this family of balls. Okay. So, check of F is what? A simplex sigma, which is a subset of P1 to Pn, is in the check complex if and only if intersection of the balls centered at Pi of radius alpha. So, you put an alpha here also. So, this is the parameter, shows the balls are of radius alpha. Okay. So, intersection of the balls centered at Pi of radius alpha have a non-empty intersection. By the way, is it a simplicial complex? First question. I kept saying it's a simplicial complex, but it is a proof, right? Why is it a simplicial complex? If T balls have a non-empty intersection, any subset of T balls will also have non-empty intersection. So, downward close property is there. So, you do not have to worry, simplicial complex, good. But then you might say, oh, what is the point of computing this? Yeah, it is a nice combinatorial, it is a combinatorial object, whether it is nice or not, who cares, but it is a combinatorial object. Why do I care about this combinatorial object? The interesting thing is, as I said, if you sample the points densely, you hope the union of balls for this object will capture its properties, specifically topological properties, topological features. What you can show is, and this is a check theorem, which I will not be proving, but it says that, well, it is not hard to prove actually, but it says that this union of balls has the same homotopy type as check complex. So, homotopy type is, again, it is a topological term, again do not have to mean, like, topological features are same. Okay. whatever be the number of holes this object have, okay, things like this. In higher dimension it gets more complicated, but there is something called topological features. Okay. The topological features of this union of balls will be same as that of this check complex. But see, the check complex is a completely combinatorial complex that you can store. Okay. A union of balls is a nightmare to store. Okay, so as with all good things, there comes a caveat. Okay. Even this is sometimes hard to store. See, here I can compute this complex if and only if I can, given some set of balls, I should be able to compute whether they are, the intersection is non-empty. This is not an easy question in high dimension, it is costly. Okay. There are variants of it, of check complex that people store, which also under some conditions satisfy some nice property. It is called Rips complex. I will not be defining it, but it is called, what is it? These families are called, what are this Rips complex fall into a family of called flag complexes. I will not be defining it, so do not worry, but kind of like even the check complex sometimes is harder to store, like harder to compute, because you have to compute intersection of balls. But it does have, if you know how to compute, no point keeping track of balls. If you are only interested in topological features, keep this check complex and you are done. This is a good thing. Okay. This is one thing. But what is one of the most popular nerves? So basically this is, let me go back. So check complex is basically nerve of the balls. Right? See the definition of the nerve. I have some collection of sets. For that I have corresponding, I have made some vertices, one-to-one relation between the vertices here and the sets here and the vertices here. Okay. And I say sigma belongs to nerve of S if and only if intersection of Si, where Vi belongs to sigma, is non-empty. I am basically doing that for the check complex, right. Check complex is basically nerve of the balls centered at different PIs. It's okay. So this is the theorem, that's what I am saying. Theorem states that the union of the balls has same topology. I don't know, I don't want to use this homotopy or anything, has same topology as the check complex. So the topological features of the union of balls you can understand, you can get by just looking at the check complex. Yeah, I really don't want to get into it because I have to define like some things that. So think of it in the following way. So right. So let's look at this. So what is the defining feature of, what is the difference between? So everyone knows what is a torus. Yeah, it looks like a donut with a hole inside. Okay, and a sphere. They are two different objects, right? Two-dimensional sphere that lives in R3, a torus that lives in R3. Okay, both are both are surfaces. They have a different topology. Okay, I don't want to get into these things, but but these distinctions you can do by just looking at this check complex. Okay. So this is how. So you are given the set of points, and then you like. So then there, see, where the theorem that you use is basically if you have this balls of radius alpha, okay, then the union of these balls have the same homotopy as this check complex. It's good. That is a good part. Okay. Then what will boil down to computing check complexes? I should be able to compute intersection of balls basically. That itself can be expensive. Okay. But let us assume I can do that. Okay. Then at least I do not have to store this continuous object. Okay. I can only store this combinatorial object and I will learn whatever topological features I wanted to learn. And the idea is if the balls are of small size, okay, then I will be able to learn the union of the balls has the same topological features as the object from which the points are sampled. So let me just give you one, okay, so let me just not prove it, but it is not possible to prove here, but one like really interesting theorem here is, So, let us say I will be vague. Let us say you have a dense point sample on a manifold. Manifold are generalization of surfaces in higher dimension. Okay. Smooth manifolds, so nice manifolds you can say. So, let us forget about smooth, nice manifolds. Okay. There exists an alpha greater than 0 that only depends on the manifold, not manifolds, this manifold M. So, this will be a function of, so alpha will be a function of the manifold M, okay, such that if you take, if the point sample is dense and if the point sample is anyway dense, if you take, so let me write this, if you take the union of balls of radius alpha on the point sample, then they have the same topology as the manifold. Then they have same topology as manifolds. So, by same topology I mean this homotopy, but okay, topology means many things, but when I am talking about same topology it means the same homotopic. The extremely interesting result, extremely foundational result now in topological data analysis. Okay. This was proved by Neogi, Smale, Weinberger around I think 2007, 6, I forgot the date. It was before I started my PhD, as far as I remember now. It was before 2008, sir. And this has been extremely influential result. Okay. So, basically now with this point sample, if I have computed the check complex and the manifold will be of the, have the same topology. This is what you want to do in data analysis, right. You want to learn features of the object from which the points are sampled, and you hope to sample enough points from the object. See, if you want to, if you sample very few points from the object, you cannot hope to learn the features of the object by sampling very few points, right. So, let us say the object is like union of two circles, and what you have done is you have only selected points from this one circle. You won't be detecting two circles by looking at point sample, right. So, you hope you sample enough points from the object. What this result says is, if the object is of particular kind, then you can learn many interesting features of the object. Good. So, yes. So, nice to, yeah, so I do not want to get into this because not the idea of this lecture to discuss this, but so this alpha basically captures the complexity of the object. You have to take smaller values of alpha and the point set have to be denser and denser if the object is more complicated. Okay. But again, I do not want to get into it too much. So, let us say I have n points in RD. I will give you another example, example 2. Okay. You can compute Voronoi diagram of each pi, Voronoi cell of each pi. What is it? All those x belonging to RD such that distance between x and pi is less than equal to distance between x and pj for all pj. So, let us call this set P, capital P, for all pj in capital P, right. This is the Voronoi cell, right, of a point. What is the Delaunay triangle? What is the Delaunay complex of this Voronoi cells? Delaunay complex is nothing but nerve of the Voronoi cells of PIs. That is it. The good thing is, if the points set are in general position, this abstract complex has a geometric representation with the same vertices, like you do not have to find separate vertices for this, right. Keep pi to pi and you have this nice complex. Complex has some other nicer properties. This Delaunay complex triangulates the convex hull of pi, right. But basically Delaunay is nothing but nerve of the Voronoi diagram. Okay? Even when, let us say if the general position assumption does not hold, okay, then the geometric representation with those as points may not be possible, but the complex is still a valid complex, because nerve is a valid simplicial complex. Okay. Again, this is slightly subtle, we can discuss it offline. Okay. So, let me discuss a bit about how simplicial complexes are stored, how simplicial complexes are stored in so let me give you one example. So let us say and this tetrahedron is present also, okay, and all its faces are present. So, this is a simplicial complex, like the edges are present, the vertices are present, the whole tetrahedron is present, and all these two edges and the vertices is present. So, you can store it as a Hasse diagram. So, what is it? It looks like this. You put empty set in the top. So, is people familiar with hash diagrams? No, okay. So, then the next level is level 1 sets. So, it is 3, 4, 5, okay, because all the vertices are there, all the 5 vertices are there. What are the edges present? 1, 2 is present, right. So, 1, 2 will be present, we will make like this. You also have 2, 3. So, 2, 3. Hash diagram is subset relation, right. Okay. So, this is how it is stored. You can go down level by level and store it. Okay. Now, so this is not that fast. Okay. Now, you have come up, people have been using something different, which is called simplex tree. I do not want to get too much into it, but I will give you some words to search yourself, or you probably already know if you have taken a course in data structure, is basically how are simplices stored. Simplices are, you think of simplices as words. Okay. So let us take another example. Okay. So let us take the same example basically. So we have this 1, 2, 3 and this tetrahedron. Okay. The simplices will be thought of as 1, 2, 3, 4, 5, 1, 2, 2, 3 like this. Okay. So, and the another one you have is 2, 3, 4, 5. So, one will be 2, 3, 4, 5. Okay. So, these are words over an alphabet, right. What is one of the popular data structure to store words over alphabet? Prefix tree, right. Prefix tree is used, and sometimes it works faster than hash diagram. Okay. So, these are how people store it. Okay. Okay, good. Okay, so, now basically we will be looking at this convex polytope for the rest of the class and / polyhedron. So, let us go to the definition first. What is a convex polytope, or sometimes we will just say polytope. A polytope is nothing but convex hull of finite number of points. Convex hull of a finite set in RD. That is it. So, what is the dimension of the polytope? What do you think should be the dimension of the polytope? How should we define it? How did we define it for simplices? There were two definitions, equivalent for simplices, right? One was number of vertices minus 1, the other one was dimension of the minimum dimension affine space containing the simplex, right? Obviously, I cannot use the definition of it makes no sense, right? See, I do not want to make distinction in terms of dimension between a triangle and a square, right, in R2. Does it make sense? In terms of polytopes. So, you want to use the definition of you want to use the geometric definition. So, you say the dimension of the polytope is the dimension of the minimum dimension affine space that contains the polytope. Okay? Pardon? Polytope are nothing but convex hull of finite set of points. Okay. So, now I want to define just like we had faces, subsimplexes and things like this for simplices, I want to define it for polytopes also. But polytope is more of a geometric object, right? As I said, like it's not it's like not a combinatorial object of points. Okay. So, you have to it's slightly more tricky to define faces, not much. So, before we define that, let's look at how do we define hyperplanes. So, what is a hyperplane in, so let's say HAB, hyperplane in RD. It looks like this, like all the x's such that XA plus B is equal to 0. So, what do we A belongs to some RD, this is basically dot product in RD and B belongs to R. So, equation of this is basically how hyperplanes are defined, right? Yes, no? Good. Then you can similarly you can define positive, which is equal to, so positive side of the hyperplane. Okay. So, this you can write it as another way to write, let me write that first and then do this. Yeah. So, another way to say it is HAB x is a function of the form Ax comma A plus B, 0 set of this linear function will be your hyperplane. Okay. Then similarly, you can define HAB plus, what should that be? All x such that HAB of x is greater than 0. Similarly, you can define minus less than 0. They are defining sides, open sides. Okay. So, let us now define faces of polytope. So, how do we define faces of a polytope? So, okay, even so before I define that, you need something called separating hyperplane of a convex body. Separating hyperplane of a convex body. Say let us convex body C. Okay, separating hyperplane. So, how is it defined? So, H is a separating hyperplane for C if 1 H intersection C is not equal to empty. So, it intersects. I said separating, I am sorry, I should use the word supporting. Okay, sorry, supporting. Okay, yeah, separating when you have two convex bodies. Anyway, so and the second one is C should be completely contained in H union H plus or minus. What do I mean by that? So, it looks like this. So, let us say this is a convex body, your hyperplane has a non-empty intersection with the convex body, and your convex body should be contained on one side. It should not be something like this. This is not a supporting hyperplane. Okay. Okay. So, now how do we define faces? So F subset of, so let us say you have again have a polytope P, which is basically convex hull of some set P1 to Pn. Okay. F will be a face, is a face, if and only if, I am purposefully putting if and only if, I do not want to prove this as a separate theorem. If there exists a hyperplane H such that F is a support, H is a supporting hyperplane of P, and P intersection H is equal to F. So, see, a geometric simplex is a polytope, right. The class of polytope includes geometric simplices. Can I get the faces of a simplex via this method? See, one way to define faces of simplex is like that combinatorially the way we did, right. You define subset of the vertex set, take their convex hull, and that will be the. But can we do it in this way? You can do it in this way. This is something you can verify. Few things you can do is like easiest case to check is like the triangle. You can generate all the faces, right, by intersecting with supporting hyperplanes, right. You can do it for higher dimensions also. So, let us do a small lemma here. So, what I want to prove is the following. I want to prove is faces of polytope P is also a polytope which is a convex hull of some, so let P be is a convex hull of this set, okay, convex hull. So let me write it as this. So let P be, so let me write it separately. So faces of P, which is, let us say, write it as convex hull of a finite set A, is also a polytope, and it will be a convex hull of some subset of A. Is this true for simplices? Yes, no? Definitionally, the way we define faces for simplices, this is true. And if we can show that basically faces, this definition of faces and the more combinatorial definition of faces in the simplices are equivalent for geometric simplices, then we are done. For simplices, we have already proved this, by the way. So, for polytopes, we have to prove it now, right. So, how do we do it? So, you can prove it by this following method. So, see, let us say F is a face of P, okay, the polytope. That means there exists a supporting hyperplane such that F intersection P is equal to F. Okay. Assume that P is contained P is a subset of H union H plus. Yeah, positive side P is contained. Without loss of generality, I can assume this, right? I can flip the equation and make it if it is on the negative side. Good. So, my claim will be F is nothing but convex hull of H intersection A. To prove. I want to show this. If I have shown this, are we done? We are done, right? I mean, this is something stronger, what I am saying here, even, right? If I can show this, I am done. So, one way is, do I have to show this convex hull of H intersection A is subset of F? Do I have to prove this? Does this need a proof? See, yeah, H intersection A is contained in F, right? F itself is a convex set, because F is equal to a convex set intersecting with another convex set, a hyperplane. And this is the smallest convex set that contains H intersection A. So, this part is done. The only thing I have to prove is this. This needs a proof. Right? Okay. So, let take a point X belonging to this. Okay. So, let the set A be P1 to Pn. Okay, good. So, I can write X as summation convex combination of with lambda I is greater than equal to 0, summation lambda I is equal to 1. See, this X lies on H. No, it's nothing to. So let me take other direction. I should take X in F. Okay. So this X lies on H, right? Because F is equal to P intersection H, right? I have to show this lies on X lies in convex. So H of X is basically 0, right? X is a convex combination of Pi's. So H of Xi is nothing but summation, I can push H inside. So this is something you have to verify yourself, but believe me, this is true. And this is just one line. You don't have to check, you can just from definition it follows. Okay, good. See, if there is some, so now if all the lambda i's for which Pi is not in H intersection A is 0, then the point X has to lie in convex hull of H intersection A. So what am I claiming? Let's go to, so let me go to page 1. See, I am writing X is equal to summation lambda I Pi I equal to 1 to n. So let us break it further. Okay. Summation Pi belonging to H intersection A lambda I Pi plus summation. So this let us call this A hat, A minus A hat Pi lambda I Pi. Right? Just broke the summation into two parts. Okay. If all the lambda i's here are 0, I will be done. Right? Yes or no? Yes. Observe that if Pi belongs to A minus A hat, then H of Pi is greater than 0. Because if H of Pi is equal to 0, that Pi should have been in this set, H intersection A. and for this Pi belonging to H intersection A, then H of Pi is equal to 0. See, when I take H inside, this goes to 0, right, because each H of Pi will be 0. I know H of Pi is where Pi belongs to A minus A hat is not equal to 0, is greater than 0. Okay? If the lambda i's, if even the one lambda I was not equal to 0, then Hx wouldn't have been equal to 0, because Hx is equal to 0. Because x lies in F, then all the lambda i's has to be 0 for all Pi belonging to A minus A hat. So, what does that mean? In the representation of x, I can forget this term completely. It is just some convex combination of this, but that means x is in the convexal of H intersection A. So, this is the proof. Why the last term is? Oh yeah. So, so the thing is, what did we do? So let me just remove this. So this is where this thing is nicer than the board. It will be difficult to remove these lines if I am doing it on whiteboard. So see, I know Hx is equal to 0 because x belongs to F, right, and F is equal to P intersection the hyperplane H. Good. And I also know Hx, so I also know this formula that we have written, right, this one, this formula, that Hx is equal to summation I from 1 to n lambda I H of Pi. So this summation itself, okay, I can write it as this term is equal to this term. Okay. Good. All of this is 0 because H of Pi is equal to 0. All of this H of Pi is greater than 0. If at least one lambda I was greater than 0, then H of x cannot be equal to 0. I would have got a positive value from here. That means all the lambda i's are equal to 0. That means that you can write it as a convex combination of points from H intersection A. So this is nice, right? I mean, this kind of says that the analogy is almost tight in terms of geometric simplices and polytopes. Obviously, polytopes are generalization of geometric simplices, right? But in terms of the convex hull, how it behaves as a face, they behave similarly, right? Good. So now you can define faces, dimension of the faces of the polytopes also, right? So what will be a 0 dimensional face? It will be a point. Segment will be 1 dimension. It does not have to be segment, it can be like an open, like something like this also it's possible, or a complete line also, that is also 1 dimensional face. Okay. So if the polytope looks like this, let us say, so it is like two intersection of two half spaces where it is open in this direction, both of them, plus side, right. It will be like everything that is contained in this, supported on this line and contained in this cone, right, all of the points. Its 1 dimensional face is the whole of this line, right. Faces of the geometric simplices were bounded, right? Segments, points, triangles, things like this. Here faces can be like infinite objects also, but that is perfectly fine. Okay. Then you go to planes, not planes, but like two-dimensional faces, like, okay. And the dimension you define in the same way, right? Dimension is, since the face itself is a polytope, the dimension of the face will be the dimension of that polytope. Okay. So, okay, I made a mistake here. This is for polyhedron, but anyway, so the thing that we are considering is convex hull. So, it will always be bounded. So, you do not have infinite thing. It will come for in terms of polyhedron, but I just messed up. Okay. So, here for convex hull it will be bounded always. Okay. But it may not be a nice face. It does not have to be always a triangle, a two-dimensional face. It can be like a square. Okay. But let us say, so basically what I said, a convex hull, a polytope will be a convex hull of a finite set of points, right. Good. So, let us assume that the set A is in general position. So, it's a point set in RD, it is in general position. So, no subset of points less than equal to D plus 1 is affinely dependent, all are independent. Okay. So, what will be the faces of this polytope? So, this point set A is in general position. What kind of faces will we see of A? Can there be a square? Let us say D is 10, let us say R 10. Can one face be a square? No, right? Because these 4 points are not in general position, right? In R 10. So, any subset of size less than equal to 11 should be in general position, right? If A is in general position, okay, this cannot happen. So, a two-dimensional face has to be a triangle. A one-dimensional face has to be an edge. Three-dimensional face has to be a tetrad. Like this. Okay. So, any subset of size less than equal to D plus 1, okay, will be affinely independent. That's it. But if that's it. So, if this triangle, let us say this square was present, these 4 points in R 10, okay, they are affinely dependent, right? In R 10. What about this? What about this? Let us say you have a this square in R 3. Then is it okay? Still it is not okay, right? Any 4 point should be affinely independent. Even in R 3 this is affinely dependent. Okay? So, even in R 3 this will not happen. But this will be a valid, these 4 points will be a valid general position point in R 2. But the faces then will not be this, this square, the faces will be these segments, right, these vertices. Right, because you have to intersect it with, in R 2 you have to intersect this object, the supporting hyperplanes are lines, right. A line can support a vertex, a line can support this edge. Okay. So, this is as a general position point, these 4 points are okay in R 2, but anything above that it will not work. But the only thing you have to remember is, if A is in general position, the faces of the convex hull of A will be simplices basically. These are what are called simplicial polytopes. So, I will be mentioning some results which we won't be proved. These are not hard to prove. It's the same way we prove the previous one. You prove these things also, but okay, we have to finish it, finish the course. Okay, so the thing is, what you can prove is any polytope P is a convex hull of its vertices. See, all the points of the set A may not be a vertex, right. Let us say the 4 points are like 5 points are like this in R2. Okay. The convex hull is this square. The center, this point, the point here, this is not a vertex. The vertex are only these things. Okay. So, what I am saying is slightly stronger than just saying convex hull of all of the set A. What I am saying, it should be convex hull of the vertices. Okay, good. Second thing that we want to use is any polytope can be represented by intersection of finite number of half planes. So, what is a half plane? So, you have this H, you have this H plus or H minus. A half plane will be like H union H plus or H union H minus. Okay. So, sometimes I denote it by this H union H plus, I will write a H greater than equal to 0, this I will write H less than equal to 0. So, what do I mean by that? So, if this is a polytope, then you can write a polytope like union intersection of I equal to some 1 to T H I greater than equal to 0. Okay. All of this needs a proof, but they are not hard to prove also. But okay. Okay, so let us see. So, now we need a similar object which is called polyhedron. Okay. So, how was polytope defined? Polytope was convex hull of a finite set of points. A polyhedron is kind of like a dual to it. How you define it? It is a intersection of finite number of half planes. So, basically a polyhedron P will be something like intersection of I equal to some 1 to n H I greater than equal to 0 for some H I's. This is a polyhedron. Something you can again show is a bounded polyhedron is basically a polytope. So, for a polyhedron also you can define faces, the way we define faces for polytopes, the same way you define faces for polyhedron. The mistake that I made with the polytope thing is polytope has always have the faces will be bounded objects, triangles, rectangles in 2D or something like this, right. But a polyhedron faces can be infinite. Okay, exactly the example that I was saying, writing like something like a half plane that goes in this direction, intersection with another half plane that goes in this direction. So, it will be like this cone kind of a structure, and the hinge, this line, supporting line is a face. Okay. Pardon? See, any faces of the polytope will be convex hull of some set of points, finite set of points only, right. Then I mean, when I was defining it, I made a mistake. It was my mistake. I confused you guys. Anyway. Is okay why it will be finite, but here it doesn't have to be finite, right? Yeah. Polyhedron. Good. So, I want to state one more result that we will be using tomorrow. So, let me see. Yeah, so let me define what is general position for hyperplanes. So the way we have general positions for points in RD, you can have a definition of general position for a family of hyperplanes also. Okay. So, let us say you have a family H of hyperplanes H1 to Hn. Okay. They will be in general position if intersection of k of them. So, like take k of them H1 Hk, where k is less than equal to d, intersection of this Hi's I equal to 1 to k, this affine space will have dimension d minus k. And if you take a set of size, if you take hyperplanes of size d plus 1. So, if you take now Hk rather than Hk, if you take d plus 1, this intersection will be equal to empty. This is how you define general position. Okay, you do not have to like, this is a definition. Okay. So, this is a notion of what is called simple polyhedron. What are simple polyhedrons? So, see, a polyhedron will be represented as I said, intersection of half spaces, right. If the corresponding hyperplanes Hi are in general position, this polyhedron is a simple polyhedron. Okay. So, let me just mention one result incorrectly, but vaguely I will not go into that detail. I will try to sketch out a proof of some duality result between Vorona and Delaunay and lifting and all this, but I will need this one small result tomorrow, okay, for simple polyhedron. Okay. So, let us say P again, P is equal to, this is almost correct, okay, something like this. Okay. Suppose I say like I is some, let I be a subset of this 1 to n, and I define this f of I, which is equal to intersection of Hi's. So, Hi is corresponding hyperplane of these half spaces, I belonging to this. It's okay. So, if Fi intersection P is not equal to empty, then Fi intersection P is a face of P. Okay. Here I am working with simple polytopes, by the way. Okay. So, P is a simple polyhedron, simple polyhedron. Okay. And the second thing is, what will be the dimension of this object? Dimension of, so let us say P is a simple polyhedron. Okay. We get by intersecting it with these half spaces Hi greater than equal to 0. Hi is the corresponding hyperplane and Hi greater than equal to 0 is a plus side, and any polyhedron you can write it like this, you orient the plane properly and you will get it. Okay. Now, you select an index in subset of index subset from 1 to n, I, capital I, and what you have this, you define is Fi, which is the intersection of I intersecting all the hyperplanes whose indices are in capital I. This is your Fi. Let us say Fi intersection P is non-empty. Suppose Fi intersection P is non-empty, then Fi intersection P is a face of your polyhedron. Okay? And dimension of this object is d minus size of I. Actually, I have written the whole thing. I thought, okay. This is something we will be using it tomorrow. Okay. So, and even more, any phase of P can be represented like this, can be obtained like this, obtained by some index set, some set I subset of 1 to n. So, I will try to explain this and then I will end. So, what are we trying to say? So, I am saying, okay, so your polyhedron your polyhedron is basically intersection of these half planes h I greater than equal to 0. Okay, good. Now, I said, okay, select some set of index set I from this 1 to n numbers, and let us say that intersection of these h i's where I belongs to capital I, intersection with the polytope is non-empty. That can happen, right? So, like let us say it is of so, the half planes were this, and this, and I have got this polytope, right, this whole thing. Okay. The directions of were like this interior. Okay. This is one H1, this is one H2, H1, H1 intersection P, H2 intersection H1 intersection H2 intersection P is this point. Okay. By the way, up to this point of the theorem, actually I do not need the definition of simple polytopes. Okay. Not this one, sorry, up to this. Being a phase, this till this, you do not need any simplicity. Okay. Now, if you are interested in what will be the dimension of the phase, can we estimate it looking at the size of I? There you need simplicity. This thing. Okay. Again, from this point to this point, you do not need any simplicity assumption. Any phase, take any phase of the polytope, even this phase, let us say, then you should have taken just H2 and you would have been done, right. H2 intersection P would have been this phase. This phase will be just H2 intersection P. The only place I need this simplicity assumption is here. Okay. I am, see, this needs a proof. I won't prove it. Like, okay, this is not a course on convex polytopes or polyhedron. I will use it to make connections between Vorona and Delaunay tomorrow. Okay. But the main idea is, how do I get the faces of a polyhedron? So, to get the faces of the polyhedron, you just have to find the hyperplanes which supports the half spaces, find some subset of hyperplanes, intersect these hyperplanes with themselves and with the polytope. If it is non-empty, then it is a face. If you have a face of the of a polyhedron, then that also can be represented as an intersection of some hyperplanes and the polytope. That is it. And this for the polytope case, the hyperplanes or the supporting hyperplanes that we were building, they are not coming from the points, right? Not exactly coming from the points. I mean, to some extent they are coming from the points also, but here you just look at those, find some subset of HIs, it will give you, and if they intersect, if the hyperplanes intersect and that intersection with the polyhedron is non-empty, it will give you a face. And any face can be, you can generate any face by this method also. That is the result. How do you do it for polytopes? You look at basically, you look at convex, you look at subset of the points, and some of them will, some subset will give, so like any face will be generated by the convex hull of the points. That does not mean if I take any arbitrary subset of A, it will give me a face, right. Even for convex polytopes, let us say, so let us say the points were like this. So, if I take the convex hull, it will be like the whole of the interior, whole of this, right. But if I have taken these two as a subset and look at that convex hull of these two, this segment is not part of the face. It is one direction only. What I am saying is, if it is a face, then there is a subset of A whose convex hull is the face. Okay. Similarly here, if your polyhedron is defined by some intersection of half planes, okay. If you take a face, so what will be this polyhedron? This will be this blue object, right. So, I am drawing it like this blue object and its interior. So, how I generate the faces? You can generate the face by taking some collection of hyperplanes that are supporting the half spaces and intersected with these hyperplanes with the polyhedron. See, that does not mean if I take arbitrary any two hyperplanes that are supporting some half spaces used for defining this polyhedron, that I am intersected with P, I will get a face. See, this object, this line and this line, they intersect at this point. And what is this? You can intersect it with the polytope, I get nothing. They are not even intersecting the polytope. Similarly, like this segment. Just taking any arbitrary will not work. But any face, there will be some corresponding hyperplanes you can take and you get it. Only for the simple polytope property I need is because I want to know the dimension of the face. I can get it by d minus I. If I know the size of I know the dimension of the face. For that I need simplicity. Otherwise, the rest of the part does not need simplicity. This needs a proof, it is not right. The other one also needed a proof, right. It was not obvious, but the proof is exactly similar, just in the dual setting it works. There it was points, you will work it for hyperplanes. So, I end here.